Hello everyone, this is Greg from ChemCore. In this video, we're going to be going through the melting point, boiling point, and solubility worksheets. They're kind of separated. I wanted to keep them separate because they're two separate concepts. So first, we're going to go through melting point and boiling point. Now, I think it's useful to remind ourselves our trends with melting point and boiling point. The first thing we should consider when trying to estimate melting point and boiling point is IMFs. And so as IMFs increase, or the strength of intermolecular forces increase, our boiling point will increase, as well as our melting point. Okay. Now, the next thing that we should compare after IMFs is polarity. Now, I realize that eventually, hopefully you guys realize this polarity is actually kind of tied to IMFs. The dipole-dipole interactions is technically a measure of polarity. Now, as we increase polarity, our boiling point will also increase, as well as our melting point. And finally, after polarity, we should measure molecular weight, or literally how big the thing is, how heavy it is. As molecular weight increases, your boiling point will increase, as well as your melting point. Now, the difference between boiling point and melting point is with surface area. So as surface area increases, or branches decrease, that's like another way of saying either surface area or branching, your boiling point will increase, but your melting point will decrease. And so I don't like to think of branching. It's kind of hard for me to imagine branching. I like to imagine surface area, so literally how kind of spread out a molecule is. As surface area increases, you have an increase in boiling point, but a decrease in melting point. It's kind of easier for me to remember that. And so I'm giving you guys that trick because maybe it'll help you as well. Now, in the first problem, we're trying to compare which alkane is predicted to have the highest melting point of those shown. Now, clearly, if they're all alkanes, they will have the same IMFs, so we can kind of cross out IMFs. If they're all alkanes, they're all nonpolar, and so we kind of can't consider polarity. Now, we should probably consider molecular weight. Now, what I would do is, since they're all alkanes, if they have the same number of carbons, they will have the same number of hydrogens. And so the answer choice A will have four carbons. B has 4 carbons. 1, 2, 3, 4, 5 carbons. Here we have 5 carbons, and here we have 1, 2, 3, 4, 5 carbons as well. And so since A and B are smaller, we can definitely eliminate A and B. Okay. And so now we're narrowed down to 3 of them, and since we already compared melting point, we now have to consider surface area. And so again, as your surface area increases, your melting point goes down. And clearly, answer choice C has the largest surface area. It's kind of the stretched out form. D has an additional branch, right? So you add one more branch, you kind of decrease that surface area. And E has the smallest surface area. You have those 2 branches, right? It's almost like a little clump. You can even see it visually. And so E has the smallest surface area, which means it will have the highest melting point. And so we're left with the answer choice E. The next problem is asking us which compound would you expect to have the lowest boiling point? Now, the first thing I like to compare is intermolecular forces. And so intermolecular forces are hydrogen bonds, dipole-dipole interactions, and London dispersion forces. Now, remember that hydrogen bonds are kind of a force of attraction where hydrogen is bonded to either oxygen, nitrogen, or fluorine. And if you looked at all these questions, you would see that A has that hydrogen bonded to nitrogen, so it does have H bonds. B has a hydrogen bonded to nitrogen, so it also has H bonds. So does C, and so does E. You're left with answer choice D that does not have those hydrogens connected to nitrogen. And so actually this should have a lone pair over here, but you'd realize it has no hydrogen bonds, which means it has the weakest intermolecular forces, therefore the lowest boiling point. In the next problem, we're asking which of these compounds would have the highest boiling point. Now, I want you guys to realize that throughout this worksheet, a lot of the boiling point and melting point questions you'll be able to get away with just by really understanding your intermolecular forces. Again, you need to understand your intermolecular forces. So if you don't, go back to Unit 1. I have a whole video on it. I feel like that's one of my favorite videos. I feel like it's a concept that not a lot of students pick up all the way, even though it's super easy. The strongest intermolecular force is hydrogen bonds, in which hydrogen is bonded to either oxygen, nitrogen, or fluorine. And so what you have to realize is now, since we know our functional groups, we can kind of use this logic to understand how different functional groups can relate to each other. I want you to understand that the 2 functional groups that we have just oxygen, so just one oxygen, or required one oxygen, are ethers and alcohols, right? Now, what I want you to realize that ethers are that oxygen is in the middle of the chain. And so that oxygen does not have a hydrogen. So there's no H bonds. There's no H bonds or hydrogen bonds. But the alcohol, no matter whether it's primary, secondary, or tertiary, that alcohol has that hydrogen on it, meaning it does have hydrogen bonds. And so no matter what your example is, your alcohols will always have a higher boiling point and higher melting point than your ethers. And so using that, let's go into this answer choice, into this question. Answer choice A, we see both of the oxygens are kind of in the middle of the chain. They're both ether functional groups. We can eliminate A. Answer choice B, we have these two ether functional groups. Again, it doesn't matter where they are. You don't care, right? The intermolecular forces don't change at all. Answer choice C, again, two ethers. Answer choice D, again, two ethers. While in answer choice E, instead of having these two ethers, you have these oxygens on the outside. Therefore, they become alcohols. Now, a long time ago, in video 1 of unit 2, we talked about isomers. And the really neat trick that I taught you is that with the same carbons, and unless there's other functional groups going on in the molecule, ethers and alcohols are constitutional isomers. And so all of these answer choices are constitutional isomers of each other. And so with the ether functional groups, you can create an alcohol with the same formula. And so really understanding your intermolecular forces will help you decode these questions. And so our answer choice is E, because we have those two forms of hydrogen bonding with the two alcohols on each side. The other answer choices do not have that. In the next problem, again, we're trying to find which compound has the highest boiling point. And so looking at it, kind of glancing at it really quickly, I do see oxygens across some of the answer choices. And so whenever I consider boiling point, anytime I see either boiling point or melting point, the first thing I think about is intermolecular forces. And if we want to find the one that has the highest intermolecular forces, let's find if one of them has a stronger intermolecular forces or hydrogen bonds when the others don't. And so visually, I see that this answer choice C has this oxygen at the end, meaning that it has H bonds, while answer choice A is literally just a hydrocarbon, so very weak intermolecular forces. B is an ether, no hydrogen bonds. D is an ether, no hydrogen bonds. And E is an ether, also no hydrogen bonds. And so you're left with answer choice C that has hydrogen bonds, and because of that, you have the highest boiling point. In the next question, again, you're looking for the highest boiling point, except this time they give you a bunch of different types of functional groups. Again, it doesn't matter. Look for your strongest intermolecular forces. I see oxygens throughout the molecule. And so what I realize is that alcohols and carboxylic acids both have hydrogen bondings, as well as amides and amines. And so I only see one of these functional groups in D, right? You see this alcohol at the end, which means you have hydrogen bonds. Answer choice A, hydrocarbon. Definitely weak intermolecular forces. B, you have an alkyl halide. It's polar, but so what? It doesn't have hydrogen bonds, and so we can eliminate that choice. C, even though you have this oxygen, there's no hydrogen on it, meaning you do not have hydrogen bonds, so you can eliminate C. And the E, again, it's an ether, no hydrogen bonds, you can eliminate it. You're left with answer choice D. In the next problem, even though you don't know how to name stuff, we already know the prefixes of certain hydrocarbons and how, through the past couple worksheets, how we can kind of change the name depending on the functional group that we have. And so what you should realize is that A, B, and C, and the E are all hydrocarbons, right? Hydrocarbons, no matter whether they're alkenes, alkanes, alkynes, they're all nonpolar. D is bromoethane, which means you have this ethane, you have the two carbons with a bromine on it. No matter how you would arrange it, it would end up polar. And so even though we don't really want to compare intermolecular forces, D is polar, the rest are nonpolar. The one with the increased polarity, or more polar, will have the highest boiling point. And so the answer choice is D. Besides that, if you were to count the molecular weight, D would be probably the heaviest. Why? Because other than kind of replacing that hydrogen with a bromine, you end up with more stuff than any of the other answer choices. In the last problem of this page, you're again looking for the highest boiling point. Let's find the one with the strongest intermolecular forces. In other words, we're kind of looking either for an alcohol, an amine, a carboxylic acid, or an amide. And so answer choice A is an alcohol, B is an amine, C is just a alkyl halide, so we can eliminate that choice. D, well, it's water, right? Let's draw water really quick. Even though it's not an organic molecule, it definitely has hydrogen bonding, and so you can keep answer choice D. And E we can eliminate. At this point, it's kind of interesting. We should compare ethyl alcohol, ethylamine, and water to each other. And so the best way to solve this problem is really to draw it. Let's just draw these 3 answer choices. We already have water drawn. And so if you were to draw them out, you would get ethyl alcohol, ethylamine, and water. You have 2 hydrogens attached to the oxygen. Answer choice A, the ethyl alcohol, only has 1 hydrogen attached to the oxygen. So you can eliminate A because even though it does have hydrogen bonds, well, the water and the amine, those 2 hydrogens, have more kind of donatable hydrogen bonds. However, then you consider kind of, okay, we have equal intermolecular forces. We both have hydrogen bonds. We should now move on to polarity. What you need to realize is because of these carbons, because of the carbons that are attached to the nitrogen, they decrease the overall polarity of the molecule. The nitrogen is not able to kind of polarize as much. It's pulling some of this electronegativity, but not as much. Even more so, oxygen is more electronegative than nitrogen, meaning that it has that stronger pull over the electrons that the hydrogens have. And the carbons are going to kind of pull some of it back, even though they're weaker, they're going to pull some of it back. And so water has the higher polarity, meaning that it has the highest boiling point. This is definitely a tricky question, but if you got it, great job, and I hope this explanation really helped. In the next problem, we're instead looking for the one with the lowest boiling point. Or we can think of it as the one with the lowest intermolecular forces. And so if I ever see hydrogen bonds, I can kind of eliminate those because they're going to have high boiling points. Answer choice A, we have the alcohol, so we know we have hydrogen bonds. B, again, the same thing. And D, we have the same thing. And so we're left with answer choices C and E, which both do not have hydrogen bonds, and so they have pretty weak intermolecular forces. The next thing that I really like to look at is how big is the molecule. Clearly, answer choice E has a whole extra carbon, and obviously 2 more hydrogens that come with it. And so we can eliminate E because of that extra carbon. It's going to increase that boiling point. C has the lowest boiling point. In the next problem, again, we're looking for the compound with the lowest boiling point. The same concept. Let's look at intermolecular forces. Answer choice A, we see those hydrogens attached to nitrogen. We know they have H bonds. Same thing with B. Same thing with D. And same thing with E. All we're left with is answer choice E, that even though it's still an amide like the rest, it does not have any hydrogens connected to the nitrogen, meaning it has weaker intermolecular forces and therefore a lower boiling point. The last problem on this page, we're looking for the one with the highest boiling point. Again, I see oxygens, and so let's find the one that has the strongest intermolecular forces. The first, A and B, are both ethers, so we can eliminate them. C and D are both alcohols, so we'll keep them, right? We have these alcohol groups at the end. E is an ether as well, kind of an interesting ether, but doesn't matter. Definitely not the highest boiling point. What we're now comparing is C and D. And what I want you to realize is that they're constitutional isomers of each other, in which C has 2 of these alcohol groups, right? We have 2 of these hydroxyls, meaning that we have 2 sources of hydrogen bonds. While in D, one of those oxygens became an ether functional group, meaning we're left with only 1 source of those hydrogen bonds. And so the one with their strongest intermolecular forces and therefore highest boiling point is C. In the last problem of the section on melting point and boiling point, we're again trying to find the one with the lowest boiling point. And so follow my strategy. Which one has the weakest intermolecular forces? Clearly, all of them are alcohols, meaning all of them have hydrogen bonds to give, while answer choice 1 is not an alcohol. There is no hydrogens connected to the oxygen, meaning there's weaker intermolecular forces and therefore a lower boiling point. And so our answer choice is A. At this point, we're going to move on to the solubility section of the worksheet. Remember that the concept for solubility is a little different. We're no longer considering kind of intermolecular forces, polarity, molecular weight, surface area. It's less things to consider. What I really want you to keep in mind while doing solubility is like dissolves like. Another way we can kind of say this is that polar solvents will dissolve polar solutes, and nonpolar solvents dissolve nonpolar solutes. Now, I want you to keep in mind that chemistry is not black and white. There's never just like a singular rule that describes everything. Everything is to an extent. Is there a certain point at which you can no longer dissolve a polar solute in a polar solvent? Definitely. But we're not really, that's more of experimental value. Within like theoretical organic chemistry, we're not going to really test you on that concept. What I really need you to remember is that if your solvent is nonpolar, you're looking for the one that is going to be a nonpolar solute if you want to dissolve the most of it, and vice versa. In question 1, that's exactly what we're looking for. A solid alkane, you don't even need the formula. Once you see alkane, you know it's nonpolar. But if you were to draw this out, you'd know it nonpolar, right? And so let's write, before even reading the rest of the problem, we know that this structure is nonpolar. The solid alkane is expected to exhibit the greatest solubility in which of the following solvents? Well, if you want the greatest solubility, you're looking for the solvent that has the most nonpolar properties. Well, answer choice A has these kind of chlorines surrounding the carbon. This is definitely nonpolar, right? If you kind of confuse with your polarity and nonpolarity, go to Unit 1. I have a whole video on it. It's there. I hope it'll help you out. At this point, you should be familiar with it. In B, you have this oxygen off the side. This is definitely polar, and so it's not going to dissolve very well. Water, you know what? I shouldn't even draw it out. Water, you should know by the back of your hand, is polar. So at this point, it should be very clear. Answer choice D, you have this amine, right? And so we have this amine, meaning that it's also polar, so we can eliminate D. And answer choice E, well, you have these, there's this two diols kind of dividing it. Now, I know it kind of looks, it looks a little polar, non-polar. No. It's polar, right? They're pulling all the electrons away from each other. It's going to be polar. Depends on how you talk about it. And because it's polar, not going to be very soluble. And so our answer choice is best A. The next problem, which of the following substances is expected to have the lowest solubility in which of the following solvents? The first thing you have to do is identify what is the polarity or non-polarity of your solvent or solute. And so we're given the solute. This is definitely polar. We're pulling all this electronegativity away. And so A, again, if you look at the structure up here, it's definitely non-polar. And so it's probably going to be pretty low solubility. Remember, we're looking for lowest solubility. In B, this is polar. And so it's probably going to be pretty soluble, so we can eliminate B. In C, even though you kind of replace one of those chlorines with hydrogen, this actually makes it slightly polar, or pretty polar actually, and so we can eliminate C. And D, you have this really long chain of carbons and these oxygens on both ends. And so even though you have this long chain of carbons, these two hydroxyls on each end make it polar. And so it's going to be pretty soluble in D. And so the solvent that has the lowest solubility is probably going to be A, right? The one that's opposite to it. So I understand that you guys haven't done acids and bases yet. However, you should know from your general chemistry course that OH is kind of your hydroxide ion, which comes when you deprotonate water. If you were to add more water into this solution of hydroxide, well, it would become more soluble. And the reason for that is water is kind of your universal solvent. Whenever you have these kind of polar compounds that are kind of ionic as well, putting water will really, really help with solubility. Like that example that I gave in the topic video of salt. Salt is an ionic compound, has great solubility. Why? Water is just cool like that. In question 4, I'm asking to mark the hydrophobic and hydrophilic portions of the molecules below. I like to kind of have a rule of thumb that chains of carbons are hydrophobic, and kind of those polar oxygens, nitrogens, so on and so forth, are going to be your hydrophilic portions. In the first structure, we have these really long chain of carbons. I don't care if it's a cyclic molecule or an alkane or alkene or alkyne. If it's a hydrocarbon, it's going to be largely hydrophobic. And so we can kind of show that this portion is hydrophobic. While this end, right, this little alcohol, and I'm going to circle maybe the carbon before it. I'm just going to make something like this. Is hydrophilic, right? Because it's that polar part of the molecule. In the next part, what you're really looking at is kind of this chain of carbons. Now, even though you have this nitrogen in between it, it's still going to be largely hydrophobic because you have a really big chain or a really big amount of carbons, while the end of it is really going to be largely polar. You can kind of show that arrow. And so this end is going to be hydrophilic. This next example is actually curated specifically. I was really excited to put this on the sheet because you'd actually be able to understand this with the example that I gave in the topic video. In the topic video, I used fatty acids as an example. This is actually a lipid. So you have these 3 fatty acids and then a glycerol backbone. And so this is a triglyceride. It's a fat that's contained in our body. I don't know if we contain all these double bonds. I'm not actually sure. Don't hold me on that. But what you should realize is the same thing that I said in the video. This long chain of carbons is going to be really largely hydrophobic. And this left ending, this polar part of the molecule, is going to be hydrophilic. In the last problem of our worksheet, we're trying to predict whether each of the following substances would be more soluble in water or in a hydrocarbon. And so remember that water is polar and hydrocarbon is nonpolar. And so if you remember that, let's identify these answer choices as either polar or nonpolar. And then, well, like dissolves like. Vegetable oil, oil in general, very nonpolar. And so because it's nonpolar, like dissolves like, it would best be dissolved in a hydrocarbon. And I think if you kind of ever tried to mix oil and water, like that example I used in the video, it wouldn't work very well. If you had to educated guess, you'd probably choose hydrocarbon. Rubbing alcohol, I don't know what the structure of rubbing alcohol is. I think it's isopropyl alcohol. Doesn't matter. It's alcohol, which means it's polar, meaning that it's best dissolved in water. Actually, alcohol dissolves really well in water. And so when you have all your drinking alcohols like vodka or tequila or beer, it's mixed with water and you don't see the difference in alcohol and water. And the next structure, potassium bromide, what you're really looking at is KBr, right? Now KBr is ionic. Ionic substances dissolve really well in water. Really well in water. And so that's something that I included in the video as well. This concludes the melting point, boiling point, and solubility worksheet. If you feel like you're unfamiliar with these concepts, go to the description, check out the topic video on this, maybe try the worksheet again. And I want to congratulate you with finishing Unit 2. In the next unit, we're going to consider a completely new concept. Maybe not completely new. You should have experience with this in general chemistry. But in the next unit, we're going to talk about the organic chemical aspect of acid and base theory. And so I'll see you guys in the next video.